Hello, so it is the 17th session, and I am a bit lazy, so the title would be Infinite Products Part 4. Third and last of this part. So we'll finish with some results related with infinite products. Last session we proved essentially two results. Well, we proved some more things, but there are two interesting results. First result called Weierstrass theorem, that I think I did not give that name. Weierstrass theorem essentially tells us that if you choose any sequence of points without accumulation points, you can always find a holomorphic function having this point as zeros with given multiplicities. And this result is valid either on C or on an open set U. It's the first result we showed. And second result, we proved Mittag-Leffler's theorem. That says that you can do the same but with poles. Essentially, you can prescribe the principal parts of poles of an infinite sequence of poles having no accumulation points, and you can find a meromorphic function f, a meromorphic function having these points as poles with prescribed principal parts. Okay. The result was stated in C, but a similar proof can be done. I'm not going to repeat the argument, but can be done if instead of C you take an open set U. Well, there are some similarities and some things that are not similar. In the proof we gave for this result, we did the following. Given a point Zn different from 0, we have 0 here, and we notice that this function Qn of z could be developed in as a power series in a disk centered at 0, and so after that we took a smaller disk and we could reason in that way. In the general case, if we have an open set, any open set U, for every point Zn, we begin as with the same argument as for Weierstrass theorem in U. So we choose first of all a point here, omega in as close as possible, but in the complement of U, and instead of developing the function at 0, we are going to develop in an annulus. Let's say we remove this closed disk here, and the function defined, the function we want to be the principal part at this pole, can be developed outside this disk, essentially. Why outside the disk? Well, how can you develop a function outside one disk? Outside the exterior of a disk is an annulus. And remember, we have a log expansion of any holomorphic function in an annulus. So we can write some expansion outside this closed disk, and after that we use very close arguments. So we have to choose some bigger disks, and outside this bigger disk you have uniform convergence, etc. So the rest of the arguments are quite close. But what is important is that the result is still valid in any open set U instead of being C. And using these two results, we can prove the final result in this context that we call theorem. Simply, that is the following one. Assume that we have, for instance, an open set U and the sequence of points. A sequence of points having not having accumulation points, without accumulation points on U. Now we're going to prescribe, instead of prescribe principal part, we're going to prescribe the beginning of the Taylor expansion. So for each of this point, take a polynomial, Pn of z minus zn. Polynomial, evaluated in z minus zn. Polynomial here, okay, of some degree mn, of degree mn. So in this condition, there exists a holomorphic function in U such that if you take the Taylor expansion of this function, so you take the power series expansion of this function in Zn, this power series expansion begins with these terms here. So the expansion here, this expansion on Zn of this function, is equal to Pn plus higher order terms. So you can prescribe to any family of points the beginning of any finite number of terms as you want of the power series expansion at those points. Well, this theorem is quite easy, assuming the previous results. Using the previous results, we're going to see this theorem is reasonably easy. So, how can we prove that? Well, first of all, take a function g. G, I think, is in my notation here. Yes, take a function g on U, homomorphic function on U, using Weierstrass theorem such that in each of the points Zn has a zero. Having a zero has a zero in each of the points Zn of order of multiplicity at least mn plus 1. Of multiplicity mn plus 1. This can be constructed using Weierstrass theorem. Okay, this function exists. Okay, second, take for instance, well, you take this polynomial here, okay, and divide, call Pn, this polynomial, divide this polynomial by g. So this is a function defined in a neighborhood having a pole, okay, it has a pole on Zn, has a pole on Zn of order at most m plus 1, because G has a 0 of order m plus 1, perhaps Pn has also a 0, so perhaps the order of the pole is smaller than m plus 1, but at most the order is mn plus 1. Pole of order at most m plus 1. Okay, so you can write this quotient as the principal part, Qn. This is the principal part of this pole, plus the rest of the terms. Let's call it Jn, the rest of the terms. This is the principal part of this pole, and these are the rest of the terms. Okay? So take G, take this quotient here, third step. Now, using Mittag-Leffler's theorem, take a function h, a meromorphic function on U, having Qn as principal parts. Has Qn of z as principal parts. So h is Qn plus the rest of the terms. But h is well defined in U, meromorphically, but well defined. Okay? So, what do we do now? Pn from here, Pn from previous, from point 2, Pn must be G Qn plus G Gn. Now Qn is h minus hn. something like this. And from here we have that G times H is equal to Pn plus G times Hn minus G times Gn. G times H is well defined. It's well defined in the whole set U. G was holomorphic and H was meromorphic, but it is defined in U. But locally around some point Zn, this function that is well defined is like this. So it is this polynomial here, and let us have a look at the rest of the terms here. Okay, Hn is holomorphic, and G has a zero of multiplicity mn plus 1. So this function here has in Zn a zero of multiplicity at least mn plus 1. The multiplicity is greater or equal than mn plus 1. And G times Gn must be more or less the same. G has a zero of multiplicity mn plus 1, and Gn is holomorphic around Zn. So this term also has a zero in order at least mn plus 1. So the terms of order smaller than mn are all there, all in this term here, Pn. So around Pn, so you have here a function defined in U, such that in the neighborhood of Pn, of Zn, begins with these terms here. So this is the beginning of the Taylor expansion of this function, is what we wanted. So this GH is the function we are looking for. Okay? So we can prescribe any beginning of the Taylor expansion. In particular, we can prescribe if you want any, let's say, any values. For instance, an example. Assume you have any open set like this, okay? Any open set like this. We're going to construct a function that is defined, holomorphically defined in this open set and can not be extended to any point beyond this set. How could you do that? You can imagine that you can take a sequence of points converging to the border like this. Take a countable sequence of points such that every point in the boundary is a limit point of this sequence. This can be constructed. Take a sequence Zn such that any point of the boundary is a limit point of this sequence. And now, using this result, consider a function holomorphic on U such that, let's say, for instance, f of Zn equal to n. This exists, such a function here. The sequence has not limit points inside U, but has but every point of the boundary is a limit point. So if you take this function cannot be extended. Cannot be extended because, well, if it could be extended perhaps to a neighborhood of this point, we have here a sequence of points tending to infinity here. Because of that, because every point of the boundary is a limit point. So there is a sequence tending to infinity, so we have to give the value infinity to every point on the boundary. So this is a way of constructing functions, of showing that, in fact, there exist functions in every open set U that cannot be extended beyond. Okay? And in many open sets, explicit examples can be constructed. For instance, there are general theorems that tells you how to construct in an open disk functions that cannot be extended to any point beyond, let's say, in this case, the boundary is called the natural boundary of the set. The function cannot be extended to any point outside or even on the boundary. So for a disk, there are quite explicit examples of that. I think the most popular one is the following series. You take the sum of z to the n. You can prove that this series cannot be extended to any point beyond. Essentially, you take rays of rational, I think of rational angle, something like this, and for those rays you see that this function tends to infinity, more or less, or it cannot be extended. It's more or less that the argument. As these rays are dense in the disk, well, they cannot be extended. It's a curious result, by the way. I'm not going to talk about that, but it's a curious result because this series apparently is a subseries of another one that you know that can be extended. For instance, this series seems to be a subseries of this one. In fact, it's this series, but with very few terms. We have removed almost every term, and this is the series 1. This represents the function 1 over 1 minus z that can be extended. Of course, there is only one point on the boundary here that is, let's say, there's a barrier here in this point, but any other point is not an obstacle. You could extend the function easily to avoiding this point. But it's very curious that if you remove almost all terms here, you obtain a series that apparently could be smaller, might be smaller in some sense, but the result is it cannot be extended. In fact, there are many results like this. There's what are called the gap series, series with big gaps. Normally there is a Hadamard gap theorem that says that under some condition the gaps, series like those, cannot be extended beyond. Series having big gaps of this kind. Okay? The series, in fact, that do not appear naturally as solution of many problems. It is a fact, for instance, for linear holomorphic differential equations, all solutions that appear naturally for those equations can be always extended, can be always analytically continued along any path that avoids some points. Which are points that are called singular points of the equation, but they can be extended beyond, along any path, in fact. So these series don't appear very naturally as solutions of many of, let's say, functional problems, but they exist. They exist anyway, these series. Okay? So they cannot be extended. Okay, this was a complement, and a couple of results I would like to mention. First of all, there is a result. Well, this theorem is a little bit theoretical, but the constructions of Mittag-Leffler's or Weierstrass theorem, it seems that sometimes we have constructed explicitly the function. So in some cases, we can use this result to construct effectively, precisely the function with given poles, or with given 0, something like this. And I will only want to mention one result that is called Cauchy simple fractions theorem. That is quite, well, I will give a short idea of the proof. I will not give the complete proof of the theorem. It's not complicated anyway. But I would like to mention this result. This result allows us to construct functions with simple poles, not in general, but at least with simple poles, simple prescribed poles, and at the prescribed pole, in fact, you have the principal part is quite easy. If Zn you want to be a simple pole, a pole of order 1, the principal part must be something like this, or alpha n, some non-zero complex number. Okay, so it's what says this theorem called Cauchy simple fractions theorem. So the following. Well, assume you have a function meromorphic on C. Assume you have a meromorphic function on C with simple poles in a set Zn. Zn is its set of poles, and all poles are simple in this set. All poles are simple, and with residues A alpha n. So this is the principal part at each of these poles. Okay? Assume you have your poles ordered in such a way that the modulus are increasing and tending to infinity if you have an infinite number. Okay? Moreover, assume that there exists a sequence of simple closed curves. So assume that a sequence Cn of simple closed curves exists such that, when I mean simple, I mean a curve which is homeomorphic to the unit circle, to S1, okay? And it's of course piecewise continuous, etc. So I don't want things like this as curves. I want things like this. Okay? Simple closed curves exist such that several assumptions. First of all, any of these points are on any of the curves. So any Zn, let's say the image Zn star intersection with this set of points is empty. Curves do not pass through any of these points. Second, 0 is inside the curve, so in the bounded connected component of the complement. A simple closed curve, you know, by Jordan curve theorem, divides the plane in two connected components, one non-bounded and one bounded. Okay? So 0 is in the bounded connected component. 0 is in the bounded connected component of C minus Cn. Okay, 3, I continue on the right, 3. If you call Rn the distance from 0 to the curve, so the minimum, the point of the curve with minimum modulus, let's say, then the length of the curve Cn is small or equal than k times Rn for some k. So this is bounded by the constant times this distance, and Rn tends to infinity. Rn tends to infinity. So essentially, for instance, this condition is verified. For instance, this is the usual case when you have some curve C1, let's say, and the rest of the curve are homothetic. You are making homothesis of this curve, so the lengths increase linearly in this case, so you have this condition. This is one of the simple cases. And finally, for the limit of the maximum of f in your curve n time divided by Rn to certain p plus 1 is 0. For certain p natural. So if all these conditions happen, then the function fn is equal to sum of, you have some Taylor expansion at the origin, Well, assume first of all that, I forgot to say, none of these points is 0, okay? The poles are different from 0. So Fn has a certain, is equal to a certain finite number of terms, k factorial zk. You have to take the p first terms here, up to p being this number here, plus alpha n times sum of alpha n, sorry, times 1 minus over z minus n minus, if you develop this at the origin, you need to remove a finite number of terms of this development, exactly the p first terms here. So remove 1 zn z zn squared minus z to the p z n p plus 1, which is the same. This term could have been written also like 1 over z minus zm times z to the p plus 1. Is the same. So f can always be written like this. Well, even the statement seems a little bit tricky, complicated. The proof is quite easy. I will only give a sketch of the proof, because the proof is quite easy. And I invite you to fill the details of the proof. The proof is quite easy. Essentially, for the proof, you need to consider this integral. You need to consider the following integral: 1 over 2 pi I times the integral along these curves Cm, well, I put here Cm instead of n, of the function of f of omega divided by omega p plus 1 omega minus z dd omega. Okay? And this integral, you can compute it using residual theorem. It has poles on 0, on z, here, and on some of the poles of f. So you have a certain family of curves, Cn. You have taken one of those curves, and some of the poles of f are inside this curve. Some other poles are outside. Doesn't matter. So you need to consider some of the poles of f. If you compute these residues here at 0, the residue turns out to be the following term, the term minus 1 over z times, is the more complicated to compute because it's not a simple 0. So you have to work a little bit to compute the residue here. So you have to compute many terms, but finally you obtain that the residue is this one. Sorry, f0 over z to the p plus f prime 0 over z to the p minus 1 plus etc. plus fp of 0 over p factorial. So here you have 1 factorial zp minus 1, the rest of them you have the second derivative over zp minus 2 factorial, etc. This is the residue at 0. It's the more complicated to compute. It's not difficult, but you have to work a little bit, okay? The rest of the points is not so complicated, because at z, the residue turns out to be f of z. Zp plus 1. You take a point z, different from 0 and of zn, and at zn, the residues is alpha n zn p plus 1 and zn minus z. So this integral is equal to this sum, the sum of this number plus this number plus sum of these terms here. 2 pi I, well, no, 2 pi I, not 2 pi I, because it's already divided by 2 pi I. Okay, and the conditions here about the length, etc., these conditions are are useful to verify that this integral tends to 0 when m tends to infinity. On the curve, here you could bound this by the minimum distance, that is the number we have called Rm. So we have some Rm m plus 1. Here you have something as Rm minus z. And we have also the length of the curve that is bounded by some constant Rm. And well, using this fact here, etc., and working a little bit, it's quite easy to show that this term tends to 0 when m tends to infinity. So finally, you have this, that 0 is equal to this sum plus this number plus this series alpha n z, then p plus 1 times zn minus z, this series. Well, from this series you take the value of the function fz and you obtain exactly the formula of the statement, this formula here. So it's only a question of working a little bit, but it's not a difficult result. I invite you to fill the result, fill the details of the proof, but that are not complicated. Okay. Well, and this allows sometimes to write precisely for many functions. For instance, for the cotangent function, in last session or in the previous one, I don't remember, we have found a precise expression developing in simple in fractions as a sum of the cotangent of pi z. Or, well, as the cotangent of pi z has a pole, sorry, at 0, in order to apply this result, we could remove the pole at 0, so take this function here. So you could apply Cauchy simple fraction theorem to this cotangent, here taking as curves the squares. As before, the square with vertices at m plus 1 over 2. You take, so this is a family of curves that are homothetic, so they are going to verify easily a condition, for instance, like this condition here. They also verify that they don't go through any pole. 0 is in the bounded connected component, there is no problem. So, well, everything. So, the only thing you need to verify is the fourth condition here, that can be verified taking p equal to 1, if I don't remember, yes, p equal to 1, yes, I think p equal to 1, let me verify at the top, yes, I think it's p equal to 1, okay, and well, if you take p equal to 1, you need to, and p equal to 0, sure, p equal to 0. P equal to 0 even. You take p equal to 0, you need to verify this. So you need to find a bound of the cotangent function on the edges of the square, and to verify this condition is satisfied. Okay? So you will have an expansion like this for the cotangent function. As p is equal to 0, here you only have one constant. That would be the value at 0 of this function here, of the cotangent minus 1 over z. You take the value at 0 of this, and here if p equal to 0, you have well, a very simple expression here also. The sum of 1 over z minus zn, something like this. You only have, if p equals to 0, you will have something as n, an integer number different from 0 of 1 of z minus n, but you can put together the term with n and the term with minus n here, and you obtain the same expansion of the cotangent as we have obtained before. we obtained before, doing the same class of arguments. But okay, this is, let's say, a systematic way of developing some functions like this. The developing of the cotangent is quite useful for many formulas. As we have seen, it's useful for the developing in infinite product of the sinus, but it's also useful for many different formulas. So this result is in some sense a practical way of using Mittag-Leffler's theorem, Weierstrass theorem, etc. when you are in the case of simple poles. Similar results could be obtained in general situations. So if instead of having simple poles you have more complicated poles, but okay, the result is not so beautiful, let's say. Okay? And finally, the last result I only would like to mention, I'm not going to enter into details, is the following. This is only for information. Remember that we have shown that any entire function can always be written like this. Zm, some function here, some entire function here, times Pm being a sequence verifying that okay. So, is there, as I have told you before, it's interesting to know which is the optimal values of P here, and is there a way also to figure out which function is h of z? We have obtained it in one case, in the case of the sinus, but we needed to develop all the simple fraction expansion for the cotangent, etc. Okay, so for some functions, it can be done that in the result is more or less the following. If you have a holomorphic function, an entire function, you can define what is called the growth order at infinity of this function. It is said that a function has growth order of at most rho if this function can be bounded in modulus by something of the like. If the function can be bounded like this, we will say that this function has growth order at most rho. And normally the growth order of a function, it is defined as the infimum of all these orders here. So this is the infimum of all the numbers here that verify this, this inequality. For instance, the exponential function has order 1, okay, or this function here has order 2, or the sinus has order 1. It's a function of exponential order 1, okay, and you can also verify that a function with order 0 must be. No, perhaps it's not. No, a polynomial has order 0 always. And if you take the exponential of a polynomial, if you have here a polynomial, any polynomial of order p, the exponential of a polynomial is entire function of exponential order p at infinity. If you have a polynomial of degree p, any polynomial of degree p. Okay, so a function, an entire function may have a finite order or not. Perhaps a function has an infinite order. For instance, e to the z is an entire function with infinite order. So no, this construction does not apply to this function. Okay, but for functions with finite order, there are very good results. Very good results. And in fact, the most celebrated result I'm only going to mention because the proof is, well, it's long. It's not, let's say, so complicated, let's say, but it's quite involved, and I would need to introduce all the theory of growth order for entire functions. And given that, there is the Hadamard factorization theorem. That says the following. Assume you have an entire function fz of order rho, and take p, the integer part of rho. P, the integer part of rho. Then you can write the Weierstrass decomposition of the function like this. So this function can be written like this, where 2. Here you can take Pn as P. If the growth order at infinity is rho, P is the integral part of rho, you can take P as the order here. And H, you can take H as a polynomial of degree P. Normally this is the most difficult part of the result, to show that H can be taken as a polynomial of degree P. So in the proof you must relate, it is needed to relate the growth order of a function with the distribution of its zeros. And there is a result that relates both concepts, the distribution of the zeros of an entire function and the growth order of the function. In some sense, if the growth order is greater, the function can have more zeros, more or less, in some sense. It's very curious. And so in that case, you can put here a fixed P and a polynomial of degree P. So this is a kind of a canonical decomposition that is quite useful. For instance, in the case of the sinus, as it has order 1, you know that the sinus of z must be z times the exponential of some polynomial of degree at most 1. So from the beginning you know that you have something like this here, times the rest. We already know that this term with p equal to 1 was possible, so we had here something like this, k equal to 1 to infinity. So you only need to figure out which values are a and b, which in this case is quite easy. Only you give some values. You give the value 0. When you have the value 0, sinus of z divided by z has the value 1. This is the value 1. So az plus b can be taken as 0, for instance. A0 plus b. So b can be taken as 0. Sorry. And you take another value, the value 1 or some other value, I don't remember, or value pi over 2, I don't remember which is the correct value you have to take, and you figure out which can you take as the value a. So it's quite easy, but you have used some powerful result. I'm not going to show this result, but it's only as an information that the result exists. And I finish here. Thank you.